12 and 0. So we expand equation 52, then we will get equation 52a. Similarly, we can expand equation 53. For example, if you look at equation 53, which is this equation right here, you can see again the index k0 supposed to go from 0, 1, 2 up until 3. So that means for that summation, you're supposed to have 4 terms depending on the index k0 equal to 0 or 1 or 2 or 3. So you expand that equation, then you will get the 4 term. This is the first term, and then this is the second term corresponding to n1 equal to 1. The first term corresponds to n1 equal to 0. And then the third term is here, which corresponding to n1 equal to 2. And the fourth term is there corresponding to n1 equal to 3. So each of the equation that we have earlier, after you expand it, you have 4 terms. Now, for a typical term corresponding to f1 n0 k0, okay, if you go back to the previous formula for f1 of n0 k0, let's see what happened. f1 n0 k0, you see you have f1 n0 k0, which is shown in equation 52a. That equation 52a actually implies that you have several equations depending on the value of n0 k0 that you are considering. So if you look at f1 of n0 k0, equation 52a, so you see, look at f1 n0 k0. If you let specifically n0 equal to 1 and you let k0 equal to 0, then what you have will be equation 52b. That's what you got, equation 52b, when you let n0 equal to 1 and k0 equal to 0. Similarly, if you let n0, the value of n0 is equal to 1 again, but now you let, let's say, the value of k0 is also equal to 1, then you will get equation 52c, and so on, so on. If you let the pair of value for n0 k0, if you let that pair equal to 0, 3, then you get another equation for f1. Similarly, if you look at the intermediate vector f2, for example, the formula for the intermediate vector f2 is given according to equation 53a, and depending on the specific value that you give for the pair of the index n0 and n1, you can evaluate the value of f2 corresponding to n0 and 1. For example, let's say suppose you want to compute f2 corresponding to n0 and 1 for the case where n0 equal to 0 and 1 equal to 1. If that is the case, then you can calculate f201 as indicated in equation 53b, as you can see from equation 53b. That equation 53b, you basically obtain it from equation 53a with the specific value for n0 and n1. Okay, so from equation 53a, corresponding to the specific value for n0 and n1, which is equal to 0 and 1. Okay, then you can get equation 53b. So to summarize it, basically we have two equations. The first equation is equation 52a. That equation will give you the computation of the intermediate vector f1. As you can see from that equation, the computation of any term such as corresponding to n0, k0 of the intermediate vector f1 will have 4 data from the previous vector f. You have to make use of the 4 data come from the previous vector f. Similarly, the computation of the intermediate vector f2 also require the 4 data from the previous vector f1, such as f1n00, such as this term from f1, such as this term from f1, and this is this term from f1. So based on that observation, those equations 52a and b, then we can present for you the graphical picture for the fast Fourier transform. Now remember, in this situation, the number of data point capital N is equal to the product of any two integer r1 times r2. And because you have two product r1 times r2, that's why you need to have a computational intermediate vector f1 and the computational for the intermediate vector f2. If you have capital N equal to the 3 product r1 times r2 times r3, then besides f1, f2 vector, you also need to have f3 vector as well. Now, in this situation, how does we start? Because we assume that the value of r1 is equal to 4 and the value r2 integer is equal to 4, which means capital N is equal to 16 data point. And because of that, that means you're supposed to have 15 index. Like for example, 16 index. N can go from 0, 1, 2, up to 15. And the definition of N, we remember earlier, can be expressed as a function of N0 and N1, as I mentioned to you earlier. So to start the process, we have the 16 value, which we know from the user input all the way up to here, 16 value. Those are the 16 data point corresponding to the index N or the index K from 0 to 15. Now, with those 16 data points that we obtain from the given periodic function f at some discretized time, the next thing we say, how do we compute the intermediate vector f1? For example, how do we compute the value of f1 corresponding to the pair 0, 0? How do we compute f1 corresponding to the pair 0, 1, and so on, so on? 16 value we have to compute. So specifically, let's say suppose we want to compute this term right here, which is f1 at the pair 0, 3. How do we compute that? That computation f1 0, 3 will require the data for previous data, which is this fellow f0, 3, this fellow here, which is f1, 3, this fellow here, which is f2, 3, and this term in here. which is F3, 3. And that is according to the graph that I show you there. Actually, this is based on the formula that we compute earlier for F1 parenthesis 0, 3. Let me see where it is. F1, 03. Yeah, you see, F1 corresponding to 0, 3 will make use of 4 previous data, which is F03, F13, F23, and F33. Each term you have to multiply with some W raised to a certain power. Okay, so F103 can compute it like that. And that is exactly what I show you in this graph. You see, F103 can be computed based on the previous 4 data, 03, 13, F23, and F33. Again, one more example. If you want to compute the value of the term F2 at 0, 1 corresponding to the second intermediate vector F2, then we can see the computation of this term F201. You have to make use of the previous 4 data come from F1, and they corresponding to F100, F101, F102, and F103. This graph in here to show you how to compute F2 at 01. I think that corresponding to the previous slide that I told you before. As you can see, F2 of 01 can be based on the previous 4 data, which is F100, F101, F102, and F103. And that is exactly I show you here on the previous data, F100, F101, F102, and F103. So, to summarize it, if the capital N, the number of sample data point, is equal to the product of the 2 integer R1 and R2, then we need to have the computation of the 2 intermediate vector F1 and F2. And because R1 is equal to 4, what it means is computation of any term in the vector F1, such as that term, will require the previous 4 data. And similarly, because R2 is equal to 4, it tells us that the computation of any term, such as this term F201 for the vector F2, will also require the previous 4 data. Okay? And that is basically the end of this lecture. Here is the acknowledgement.